good to have sound, you know. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for these students, and just ask you just bless our work today. Help us to just understand a little bit more about the Jordan form, Lord. In your name I pray, Lord Jesus. Amen. Okay, so today I wanted to... Now, I'm sure there's a proof in Chapter 7 using some sort of Jedi mind trick, but I thought it would be healthy for us to prove linear independence is implied by the K-chain conditions. So let's try to work on that. So I'll start with, let me just start with like a 3-chain, and then we'll see if we can go from there. All right, so let's suppose that we have V1, V2, V3, for which t minus lambda v1 is equal to 0, t minus lambda v2 is v1, t minus lambda v3 is v2, right? So this would make v1, v2, v3 a 3-chain with eigenvalue lambda for the linear transformation t, right? So suppose we want to show that this is in fact, if these are non-zero vectors, that it is necessarily the case that these are linearly independent. How would we prove that?
But do you prove by contradiction?
Proof by contradiction, I kill you. So we will set C1 V1 plus C2 V2 plus C3 V3. We could talk about proof by contradiction in my office hours, but I don't have enough time in class for that. So there's that. So we assume this, right? And then what I'm going to do is I'm going to operate by t minus lambda squared. So I get C1 t minus lambda, times t minus lambda v1, right? Plus C2, I'm pulling the constants out because they can, right? T minus lambda times t minus lambda v2 plus C3 times t minus lambda v3. And that's equal to 0, right? Because t minus lambda squared acting on 0 is 0, because t minus lambda squared is, after all, the composition of linear transformations, which is again a linear transformation, as we proved back in the day. So how does this simplify? So what you got is 0, right? This is by assumption 0. And so we have C2 t minus lambda times what, acting on what? This is by assumption V1, right? And this is what? By assumption V2 by the chain conditions, right? All right. But then what's next? Yep, again, so, yep, yet again, 0. And this is C3, then that's what? V1 equals to 0. And so I'm assuming at the outset that these are all non-zero vectors, okay? If they're 0 vectors, then the claim that they're linearly independent is not true, all right? And they're also not a chain non-zero vectors, all right? So if this is a non-zero vector times C3 equal to 0 by like fundamental discussion vector space, scalar vector product 0 implies either one or the other 0 or both, but V1 is non-zero, so this tells us C3 is 0. Great. Now what? Right. Exactly. So instead of doing t minus lambda squared, rats, we can do t minus lambda acting on, I'm going to do it this way this time, guys, for a change of pace here. Of course, what should I do even before I do anything else? I should remind myself, I already showed this piece is 0, so we don't have to look at that, right? And so what do we have? We've got C1 t minus lambda V1 plus C2 t minus lambda V2 equals to 0. But I think you guys know what's going to happen here. This is by assumption 0, and that is by assumption V1. So we get what? C2 V1 equal to 0, which tells me that C2 is equal to 0.
Then you just plug them in and you get C1 V1 equals 0 and then C1 is 0.
Right, now returning exactly, if we give this thing a name, say Pac-Man, right? Returning to Pac-Man, we have, like you said, C1 V1 plus 0 equal to 0. So that tells me C1 equals to 0, right? So now we got C1, C2, and C3, they're all 0. So conclusion, thus V1, V2, V3 is linearly independent, right? Because we took a linear combination of them, we set it equal to 0, and we gave evidence that all of the coefficients are necessarily 0 on the basis of the data. If you understand this proof, you probably should understand how to prove a k-chain is linearly independent, right? So like example 2, if I have, V1, V2 all the way out to Vk, where t minus lambda V1 is equal to 0, and t minus lambda times Vj plus 1 is equal to Vj for all j equals to 1, 2, all the way out to k minus 1, I suppose. Right? Then that's what I mean, non-zero. That's what we mean by definition a k-chain to be, right? So starting move, oh, did you already? Thanks, Sam. So suppose that the sum I equals 1 to k of ci vi is equal to 0. Right? And then what I'd be inclined to do, like there's two different ways to go here. The one way would be to assume it's true by give an induction proof. But what I'm more inclined to give you the proof of at the moment is just a gory calculation. In other words, just say, well, we can write the product, right? We can multiply by t minus lambda to the what? To the, what did we do? We did squared, so here we do k minus 1, right? And that, by properties, first of all, that's equal to 0. Since that's acting on 0, gives it 0. And then over here, I can pull the constants out because it's linear transformation. And I have t minus lambda to the k minus 1 power acting on VI. Right. But the smart thing to do before you did this would have been to prove a lemma. What would the lemma be? Well, yeah, I mean, so t minus lambda, how about this? T minus lambda to the p acting on Vp equal to what? 0, right? It's true for 1. It's true for 2. We worked that out the previous class, actually, right? It's true for 3. So, like, the way this works is in the k-chain, the pth level is a generalized eigenvector of order p. So you have eigenvectors of order 1, just plain old eigenvectors, eigenvector order 1, order 2, all the way up to order k, right? So you can say a little bit more than this, right? Because you can actually say that t minus lambda to the j, well, let me find j acting on Vp equals to 0 for j greater than or equal to p. Because if it's true for p, it's true for p plus 1 and p plus 2 and so forth and so forth. You know? So if you have this little lemma in mind, then this calculation becomes very easy, right? Because, you know, you need what? You need k minus 1 to be what? The flip side of this is t minus lambda to the j acting on Vp is not equal to 0 only for what? For j less than or equal to p minus 1, right? So you need k minus 1 to be what? Less than or equal to, you know, I minus 1, right? Because this is the j, and that's the p, and only non-zero outside of this case. Which is just a way of saying the only thing in this whole summation which is non-zero is what? K. So this is just ck times t minus lambda to the k minus 1 acting on Vk, right? But then, of course, we can use the chain conditions, right? I mean, you could say more. There's like a Uber lemma, and it'd probably be good to like sort through that for the sake of, you know, ease of calculation when we do differential equations about a week from now. It'd be handy to have these all in hand. But tell you what, we'll work those out when we get there. I'll just do it in steps here. It'd be kind of boring. So we've got ck t minus lambda to the what? K minus 2, Vk minus 1, right? And then ck t minus lambda to the k minus 3, Vk minus 2, right? And this keeps going, right? We get to what? Eventually we get to well, when let's see here, let me stop right before the end of it. Suppose k minus 3 is equal to 1, then k minus 2 is equal to what? 2, right? So eventually we get to t minus lambda times v2, which then, of course, last step, ckv1, just like we did over there, right? In fact, every time we ended with the eigenvector at the end of the argument. Yeah.
Wouldn't that last several lines be unnecessary because if we have the lemma that says that it's non-zero for j less than j less than, because if the transformation on that vector is non-zero already, we don't.
Oh yeah, sure. Yeah, fair enough. If I know that this is, I mean, you know that's non-zero. Yes, I'm just saying explicitly it's that. That matters to us when we get to like calculating the matrix exponential. We'll actually want to be able to simplify it to write out the formula. So I'm partly anticipating that. I'm not just thinking about the proof at the moment, truthfully told. But anyway, so this is equal to, but yes. So that's equal to 0. So this implies ck is equal to 0, right? But without loss of generality, we can repeat this argument, right, to the next thing down, and then we can prove ck minus 1 is 0, and so forth. So basically, you know, by a similar argument. Now this is not a good proof, right? This is not a great proof. You can improve this proof in terms, you know, of rigor, if you like, by recasting it as a formal induction, right? And you could just prove the induction step and have it all nice and tidy and neat and totally correct. Actually, is it totally correct? I mean, that depends on the audience, right? Proof is, what's the right proof depends on your audience. So if your proof, if part of your audience is, part of the intent of your proof is to teach your audience how to do a certain calculation, this might be a better proof than the formal induction proof, which would give you less an idea of how to calculate things. That's part of the reason I'm doing this, is to give you a kind of a window into how these chain conditions work. Anyway, that's all I have for that. So I just wanted to make sure I did some proof today, and that was it. So I needed to define something else for you guys. So this is from, let's see here, technically section 7.3. I'll give you a definition. Oh, I'm trying not to, this board's got stupid, sorry Sam, I'm gonna come back over here because half the time, unless I'm standing right where I need to, like if my shadow's not in front of the board, you can't see over there. It's so glary because we've lost just enough of the, you know, the window shades back there that it doesn't quite work. Now, so I think the book has a more clever way to prove the linear independence of these chains. But I think the way we did it today is healthy and good for you to see, so I have no regrets. So definition, what's the minimal polynomial? Definition, let T be linear transformation on finite dimensional vector space V over F, all right? A polynomial P of T, so this would be with coefficients in the field, all right? It's called a minimal polynomial of T if P of T is a monic polynomial of least positive degree for which P of T is equal to, well, he calls it t sub 0, but this he means I usually would just say 0, the 0 transformation. All right? So right away, the language in this definition is unnecessary, part of it, because you don't need to talk about, oh man, you don't need to talk about a minimal polynomial. You could erase this, and you can just put a the right here, because it's unique, okay? The minimal polynomial. And here's the major theorem about it that comes right next in the book, is like number 1, it's unique, okay? And number 2, P of t divides the characteristic polynomial t, where, as usual, characteristic polynomial t of t would be equal to the determinant of big T minus t in my current language. Let's get nuts. I've avoided writing this all t all the time expression by introducing polynomials in S at various points in this course, but let me just face the music here. There it is. A lot of times the book is writing t times I to emphasize that there's an identity operator there. I just get really tired of writing it all the time, so I'm just writing it like that. So you can put an I there if you think that's more clear. And it certainly is. All right. Although I would say that's the identity map. So if I really was going to be clear, I would probably write this, because I like to distinguish between the matrix I versus the identity map on V personally. But, anyway, I'm not even writing the I, so what room do I have to complain? So how do you think you find the minimal polynomial? And by the way, same definition for a matrix, right? Same definition for a matrix. So if we wanted to talk about a matrix, we would have P of A is equal to, 0 for the minimal polynomial. Yep.
What is the vertical bar in the second?
Divides.
Okay.
So the minimal polynomial, divides the characteristic polynomial. But let me put a finer point on that. It's better than that, actually. Actually, they share the same zeros. That is theorem oh, come on. Is that not here? Well, it's true. Where is it in here? 7, where? 714? I'm just not seeing it. Oh yes, thank you. 714 literally says it. I'm just not seeing it. I'm a dummy. Okay, so how do you find the minimal polynomial? Yep.
Find the factors of characteristic polynomial.
So find the factors of the characteristic polynomial, and then just plug it in and see what happens, right? What do you guys think? If we do the Jordan form, would that have any connection to this? What do you think? Like, let's try to find the minimal polynomial for some matrices in Jordan form. That should be pretty easy as it goes. So like, let's start out real simple. Example, what am I on? 3? Yeah. Let's say we have A equals to 2, 1, 0, 2, 3, and 3. This is not too simple, but not too bad. Everything else 0. So what is the characteristic polynomial here? We've got t minus 2 squared and t minus 3 squared, actually. So this means that here's possible candidates for the minimal polynomial, right? So we could have p of t. I usually use m for the minimal polynomial. Do you guys mind if I just don't do that here? Can I ignore the book and make it m for minimal? Let me do that. Because, all right, I mean, it's not in my notes. My notes are not complete yet, guys. So, and I usually make the characteristic polynomial actually p. So, make sure I don't leave any of these out. M. Beep bop, beep bop. M for minimal. What does monic mean? Do you guys know? No. Monic simply means that the leading coefficient is 1. That's it. It's not bad. So this is my p of t, all right? So that means the m of t could conceivably be what? Your choices are like t minus 2 times t minus 3, right? Or t minus 2 squared times t minus 3, or t minus 2 times t minus 3 squared, or what? Or it could just be literally the same as the characteristic polynomial, right? Logically speaking, they have to share the same zeros, so you have to have at least one t minus 2 and at least one t minus 3 factor, all right? But how do you decide which one of these it is? Well, you just have to calculate. So like, what's a minus 2i here is what? Mm-hmm. Yeah, 1, 1 here, right? And what's a minus 3i? So we got minus 1, 1, 0, minus 1, and zeros. I think at this point, did we ever talk about block multiplication in here? I don't know if we did or not. Now is the time to do it, though, for sure. So, like, let me write these in terms of blocks and show you how this works. So, like, see, a minus 2i in terms of blocks is equal to what I called n2, direct sum, the identity, 2 by 2 identity, right? And on the other hand, a minus 3i is what? I'll just write it out. It's minus 1, 1, 0, minus 1. I mean, technically, that's the Jordan block for minus 1, 2 by 2, right? But whatever. And then plus what? Well, plus 0. The 2 by 2 is 0, right? So the way block multiplication works, guys, is if you have m1 plus m2, and you're multiplying it by n1 plus n2, not the nilpotent 2, but just labeling, all right? If these are the same size, if these blocks are matching dimensions, the way block multiplication works is you just simply multiply the blocks, right? So this is sort of the analog of like how you multiply diagonal matrices, right? But block diagonal matrices multiply in the same way that diagonal matrices multiply, right? Like, you know what I'm talking about? If I have m1, m2, and I multiply by n1, n2 like that, how do you multiply them? Well, m1, n1, right? m2, n2, just like that, right? So it's the same. The block diagonals, they share characteristics like diagonal matrices. This is one of them. So this is block multiplication. And if I use this, then you can start to see things, right? Like, what's a minus 2i squared? So you end up doing what? You square each, right? What's n2 squared? We talked about this the other day. The nilpotent matrix of order 2 squares to 0. So that gives us 0, the 2 by 2 0, direct sum with the identity, 2 by 2 identity. On the other hand, what happens when we take a minus 2i times a minus 3i? How's that work out? So we've got n2 direct sum I2, right? Times what? Times minus 1, 1, 0, minus 1, direct sum the 0 matrix, yeah? So that would give me like 0, 1, 0, 0 times minus 1, 1, 0, minus 1 for the first thing. Direct sum, well, I2 times 0 is just 0, right? So what do we have here? We've got 0, 0, minus 1, 0. Direct sum 0, right? I'll write it out this time. The larger point here is that this is not equal to 0, right? So this rules out the lowest order possibility. The minimal polynomial cannot be just t minus 2 times t minus 3, right? Because this matrix is non-zero. But what can it be? What if I look at a minus 2i squared times a minus 3i? What happens there? We get 0 plus the 2 by 2 identity, right? Times the 2 by 2 identity, direct sum 0. Did I do that right? I'm not sure I did that right. Give me a second here. My bad. It's not the 2 by 2 identity there. What do we get? It's that uglier thing, isn't it? It's what? It's this minus 1, 1, 0, minus 1, right? Don't let me be incorrect. So that's what it is, though. The thing is, you see you have a 0 here, and you have a 0 here. So when you do block multiply, you get 0 plus 0, otherwise known as 0. So this tells me, by just rote calculation, that the minimal polynomial in t is simply t minus 2 quantity squared times t minus 3, like that. Not really. But we'd like to understand the interplay between the minimal polynomial and the characteristic polynomial and what it says about the existence or lack thereof of generalized eigenvectors. So it's another way of looking at what information does the Jordan form have in it and what can we learn about that. But no, as far as I know, there's no really, I mean, you just have to calculate. Yeah. As far as I know, that's the only way. Short of like somebody giving you some kind of like, you know, sneaky hint of some sort or another. But so can you guys tell me what 4 by 4 matrix would pick up as its minimal polynomial the other ones I wrote? Like, now that we've done this calculation, do you have enough of an intuition about what's going on here? Oh, thanks. That we could maybe write down one that would require, I mean, I can, I'll show you. So this, something like, there's more than one choice, but certainly this would do if I had 2, 2, 3, 3, 2, 2, 3, 3 on the diagonal, like that. If I subtract 2i, it'll clear out this. If I subtract 3i, it'll clear out that. And when I multiply a minus 2i times a minus 3i, I get 0. This one, we just worked out. That is, in fact, this is the one. Check. This, by symmetry of the argument, you can figure out it's got to be what? 2, 2, 3, 1, 3, right? Like that. That would have that as a minimal polynomial. This one, what's it going to be?
That one will have a 1 for both.
Yeah.
2
right.
quadrant times 3 quadrant.
Yeah, it's going to be like that. Because you're going to need the square, you're going to get a nilpotent piece when you look at a minus 2i and a minus 3i, or they're both going to pick up a nilpotent piece respectively in the upper and the lower blocks. In order to get those to go away, you're going to have to square both of those. So we need that. Now, but the thing is, there's not a one-to-one correspondence here. All right. First of all, I could reorder the blocks. Right? I could have done 2, 3, 2, 3. Wouldn't have changed a thing. I could have done 2, 2, 2, 3. Would also have not changed a thing. I could have done 3, 3, 3, 2. Still wouldn't have changed a thing. Over here, I could have erased this 2 and made it a 3. Wouldn't have changed a thing. This I'm kind of stuck with, although I could flip the order of the blocks, of course. You know, I do have that freedom. So in the past, I've asked like all possible Jordan forms with this minimal polynomial. I regret those questions. I regret those. Those are evil. There's just so many cases. So what I should say is give me 3 cases or something like this, you know. But then I have to figure them out in order to grade it, you know. Anyway. So the minimal polynomial is interesting, and it's a fun thing to look at because it... Okay, well, how about this? Can you guys tell me what is the minimal polynomial if the matrix is diagonalizable? Mm-hmm.
The characteristic polynomial, but all its factors just have power of 1.
So just like the characteristic polynomial, but all of the factors are only 1. That's right. So the minimal polynomial, being the product of distinct linear factors, is how we would characterize diagonalizability of the transformation. It's kind of neat, you know? We've just reduced the problem to polynomial algebra in some way. Now, as Toby has pointed out, the devil's in the details for a specific example for sure, but it does give you kind of neat result. I want to show you guys something else. So if you study the proofs in chapter 7, one more thing for today. One of the things that's used is, I did have a homework problem on minimal polynomials. I wanted to at least spend some class, not just drop that on you in the homework, right? So I don't think the homework problem is terribly difficult or anything, but the other thing, I think I said that you wouldn't have to calculate a Jordan basis. That's not entirely true. I do think you should be able to calculate Jordan bases for like low dimensional transformations. Like if the dimension of the transformation is like less than about 4, I think that's very much within your grasp. You can work it out. Like in the process to do that, you just find all the eigenvectors that you can, and whenever you don't have enough, go looking for generalized eigenvectors. Try to like solve the chain condition. That is dangerous advice in general, because in general that method fails, because what happens is the eigenvectors from different chains get intertwangled at lower orders, and so when you go looking for the higher order one, it's hard to untangle them as you go up. That's hard to appreciate unless you have like a 10-dimensional example. My brother was unaware of this, teaching linear algebra for like several semesters. He was teaching at Rutgers, and he just managed to work to like, he just happened upon an example where like finding all the eigenvectors and working your way up didn't work mid-class. Like it just happened to him. He's like, but so that's how I know about it. Otherwise, I would just think you always just find the eigenvectors and work your way up until I read a book, I guess. But so one of the things that's central to the arguments in your book is there's arguments to prove that the so they look at something like t minus lambda to the p versus t minus mu to the q, something like that, where these are distinct, and arguments are made about this being one-to-one and onto with respect to that its kernel or something like that. And I want to try to like show you a little bit about what's going on there, because something really interesting. So check this out. And so this is just a little bit of an advertisement for Math 422. The greatest common divisor of x minus 1 squared and x minus 3 is equal to 1. These polynomials are relatively prime. And by an analog of the Euclidean algorithm for polynomials, you can show that you have this relation. This is the analog of Bazou's theorem, or Bazot's theorem, I don't know, whatever, I'm not French. Minus 1/4 x minus 1 squared minus 1/4 times x minus 1 times x, well, my bad, x plus 1 times x minus 3 is equal to 1. So in fact, my brother has a calculator. If you go and if you plug these in, it shows you the corresponding relation like this. Yeah. So if that's true, what does this matter? Every polynomial identity corresponds to a corresponding identity for your operator. I can evaluate this on t. It tells me something. It tells me that 1/4 t minus 1 squared minus 1/4 t plus 1 times t minus 3 is equal to the identity. Now here, let me confess, my t is equal to left multiplication by a, where a is equal to 1, 0, 0, 1, 3, 0, 0, 1, 1. Hey, at least I'm giving this as a class example rather than a homework, right? A equals this. And if you look at this, the characteristic polynomial of a is actually equal to minus parentheses t minus 1 squared times t minus, let me do x. x minus 1 squared times x minus 3. That's fairly obvious from this, looking at it. All right. So that's why I'm calculating this particular identity, because it's related to this transformation. So what happens here? If you think about how this formula works. Think about what if you have V in the generalized eigenspace with eigenvalue lambda equals to 1 versus, say, V, an element of the eigenspace with lambda equals to 3. How do those two different kind of vectors behave as you hit them? See what happens here? An eigenvector dies here. The generalized eigenvector, they all are killed by this. So these are actually projections onto the generalized eigenspace of lambda equals to 1, or over here, lambda equals to 3. And something else that's fun to check is if you take 1/4 times a minus I squared minus 1/4 a plus I times a plus 3i. So here's the corresponding, plug the matrix into the same polynomial, right? then I worked it out, and like a minus I squared works out to 0, 0, 0, 2, 4, 0, and 1, 2, 0. And then you've got minus 1/4, and I'll do the multiplication for you because we all want to start the weekend. Minus 4, 0, 0, 2, 0, 0, 1, 2, minus 4. When you multiply those out, and what's that give you? Yeah. So the complete proof of the, yeah. Uh-oh.
When you're calculating that, should it be minus 1/4 a plus I times a minus 3i or plus 3i?
Oh yeah, that was minus. I'm sorry. That's what I actually calculated. I just typo here. Thank you. So if I was to, I know you guys are happy if I use pi, so let me do that.
Your actual numbers.
No, not that kind of pi. So this would be the projection, I believe, onto the eigenspace with lambda equals to 3. And I believe this character over here is the projection onto the generalized eigenspace with lambda equals to 1. Right. Because it is true that R3 is it's the direct sum of the generalized eigenspace with eigenvalue 1 and the eigenspace with eigenvalue 3. And these will project, you know, onto these different spaces as appropriate. They'll actually pick out the part of the vector which lies in here or in there as appropriate. If you wanted to take a general vector in R3 and say, hey, which part of it lies in the eigenspace, which part of it lies in the generalized eigenspace, you could use those projection maps to select the appropriate part. So we can calculate projection maps here if we knew about this Euclidean algorithm business and how to calculate these kinds of equations. We could use that to set up projections. But we're going to see in the next story arc in the course that there's something more beautiful in terms of like orthogonal geometry and these things. When we have some inner product space stuff coming into play, this stuff gets a little bit more interesting, I think, because I know you guys don't know this algebra, right? Right, yeah. I might put it in the homework, but that's only because I will also provide a link to my brother's website, which will calculate it for you. In fact, his website will calculate these kind of things not only for like real coefficients, rational coefficients, but also for like z mod 5 or something. It's set up for a wide variety of different cases. But actually, to completely finish the Book's argument, we'd also need to do this for like more than 2 factors. Like, what if you had 3 things, like the GCD of f, g, and h? You know, f of x, g of x, and h of x. There's a generalization of this theorem to k-fold things, and that's actually what's used in the proof in the book if you look. So anyway, thanks guys. Have a good weekend.